Numerical climate models use quantitative methods to simulate the interactions of the important drivers of climate, including atmosphere, oceans, land surface and ice. They are used for a variety of purposes, from study of the dynamics of the climate system to projections of future climate. Climate models may also be qualitative models and also narratives, largely descriptive of possible futures. Quantitative climate models take account of incoming energy from the sun as shortwave electromagnetic radiation, chiefly visible and shortwave infrared, as well as outgoing long-wave infrared electromagnetic. Any imbalance results in a change in temperature. Quantitative models vary in complexity. Box models are simplified versions of complex systems, reducing them to boxes linked by fluxes. The boxes are assumed to be mixed homogeneously. Within a given box, the concentration of any chemical species is therefore uniform. However, the abundance of a species within a given box may vary as a function of time due to the input to the box or due to the production, consumption or decay of this species within the box. Simple box models, i.e. box model with a small number of boxes whose properties do not change with time, are often useful to derive analytical formulas describing the dynamics and steady-state abundance of a species. More complex box models are usually solved using numerical techniques. Box models are used extensively to model environmental systems or ecosystems and in studies of ocean circulation and the carbon cycle. They are instances of a multi-compartment model. A very simple model of the radiative equilibrium of the Earth is where and the constant pi r2 can be factored out, giving solving for the temperature. This yields an apparent effective average Earth temperature of 288 K. This is because the above equation represents the effective radiative temperature of the Earth. This very simple model is quite instructive. For example, it easily determines the effect on average Earth temperature of changes in solar constant or change of albedo or effective Earth emissivity. The average emissivity of the Earth is readily estimated from available data. The emissivities of terrestrial surfaces are all in the range of 0.96 to 0.99. Taking all this properly into account results in an effective Earth emissivity of about 0.64. This simple model readily determines the effect of changes in solar output or change of Earth albedo or effective Earth emissivity on average Earth temperature. It says nothing, however, about what might cause these things to change. Zero-dimensional models do not address the temperature distribution on the Earth or the factors that move energy about the Earth. The zero-dimensional model above, using the solar constant and given average Earth temperature, determines the effective Earth emissivity of long-wave radiation emitted to space. This can be refined in the vertical to a one-dimensional radiative convective model, which considers two processes of energy transport. The radiative convective models have advantages over the simple model. They can determine the effects of varying greenhouse gas concentrations on effective emissivity and therefore the surface temperature, but added parameters are needed to determine local emissivity and albedo and address the factors that move energy about the Earth. Effect of ice albedo feedback on global sensitivity in a one-dimensional radiative convective climate model. The zero-dimensional model may be expanded to consider the energy transported horizontally in the atmosphere. This kind of model may well be zonally averaged. This model has the advantage of allowing a rational dependence of local albedo and emissivity on temperature. The poles can be allowed to be icy and the equator warm, but the lack of true dynamics means that horizontal transports have to be specified, depending on the nature of questions asked and the pertinent time scales. There are, on the one extreme, conceptual, more inductive models, and, on the other extreme, general circulation models operating at the highest spatial and temporal resolution currently feasible. Models of intermediate complexity bridge the gap. One example is the Climber-3 model. Its atmosphere is a 2.5-dimensional statistical dynamical model with 7.5 degrees times 22.5 degrees resolution and time step of half a day. The ocean is MOM3 with a 3.75 degrees times 3.75 degrees grid and 24 vertical levels. General circulation models discretize the equations for fluid motion and energy transfer and integrate these over time. Unlike simpler models, GCMs divide the atmosphere and/or oceans into grids of discrete cells, which represent computational units. Unlike simpler models which make mixing assumptions, processes internal to a cell, such as convection, that occur on scales too small to be resolved directly are parameterized at the cell level, while other functions govern the interface between cells. Atmospheric GCMs model the atmosphere and IMPO